Okay, so today I will show you how you can enhance your project with potentiometers by using potentiometers that glow. That's right, and not just the potentiometers but also the knobs are glowing, which means that you can then use your project in the dark environment. But even if you don't plan to use your project in the dark, I think it still looks nice. And all you need is this special kind of potentiometer, which has this handle made from transparent plastic. So if you place the LED below the potentiometer, it will shine through. And there is actually the hole inside, so you can put it all the way in. So today I will show you how you can use this potentiometer with the Arduino UNO and how to create a custom PCB in the form of the Arduino UNO shield. And I have also a second PCB which works as a front panel. Both of those PCBs are manufactured by PCBWay, who is also a sponsor of today's video. So thank you PCBWay, but more about them later in the video. For now, I want to use just this potentiometer with the Arduino UNO without any custom PCB, but that's kind of hard, mainly because the spacing for those pins is not breadboard friendly. Thankfully, when I've ordered the potentiometers, there was an option to also order this small PCB on which you can place the potentiometer, but also the LED and the resistor. And then there are those pins down there which do have the same spacing as the breadboard. I haven't found any datasheet for this PCB, but since those traces are quite visible, you can easily see what is connected to which pin. On front it says plus 9 volts, but I believe that's only because those potentiometers are meant to be used with guitars and guitar effects, and they often work on 9 volts or 12 volts. But I don't think there is any reason why we cannot use this with our 5 volt Arduino board. If you take a closer look at the potentiometer, it says B5K, which means it's a 5K potentiometer. I usually use 10K potentiometers with the Arduino project, but the 10K potentiometer version was sold out. Again, I don't think this will make any big difference. So once I've soldered the 3mm LED, the 220 ohm resistor and the potentiometer and the header pins, it might look something like this. The pins labeled 1, 2 and 3 are for the potentiometer, pin 2 being the signal and then pin 1 being the ground and 3 being the 5 volts or the other way around. This depends on whether you want to increase the value by going clockwise or counterclockwise. And then we have the ground, this is for the LED, and 9 volts, again this will be 5 volts for our LED. And you can test the LED with the coin battery. If you place it between those two pins, it should be shining. As for connecting this to the Arduino UNO, you can use jumper wires, but what I usually like to do is to use this breadboard shield. It's very cheap and it's perfect for simple projects. I've connected it in the way that the pin 1 goes to ground, then the pin 2, the signal from the potentiometer, goes to analog input pin A0, the pin 3 goes to 5 volts, the ground for LED goes to ground. The 5 volt for the LED could go to any digital pin, but I would like to use a digital pin that has the PWM enabled, the pulse width modulation, because then I can change the brightness of the LED. And the pins with the PWM has this small wave icon next to it. So I can, for example, use the pin number 9. And with everything connected, we can start writing the sketch. And I will not start in the Arduino IDE, but inside Vocway, which is a free online Arduino emulator, because I can create a new Arduino project using the Arduino UNO. And it also supports the potentiometer, which I will add to the project, and it also supports LED, which I will add as well. I just need to connect it in the same way as for the real Arduino, so the potentiometer ground goes to ground, the signal goes to pin A0 for the analog input A0, the VCC should go to 5 volts, and then the LED cathode should go to some resistor, so I'll also add the resistor. The value is not that important for the simulation, so I just connect it to the cathode and then connect it to the ground. And as for the anode, we've already connected it to pin number 9, so I'll do the same thing, connect it to the pin number 9. Let me just change the color of wires so they are more visible, and now we have the very same connection as for our real Arduino. The first thing is to set the pin modes either to inputs or output, so for our LED, the pin number 9 should be output. I will set the pin mode of pin number 9 to be output, and then for the pin A0, this should be input, so pin mode of pin A0, it should be input. What I want to do is to read the value of the potentiometer, and based on this value, I want to set the brightness of this LED. So I'll create a new variable called potentiometer value, and read it using the analog read function of the pin A0, and then to set the brightness of the LED we can call the function analog write. That will set the PW signal for the pin 9, and it should go between 0 and 255. Now our potentiometer value goes between 0 and 1023. We need to remap this value using the map function, so our potentiometer value, which goes between 0 and 1023, should be remapped to go between 0 and 255. And I guess that's all that we need, so let's run the simulation and see what happens. So when the potentiometer is all the way to the left side, the LED is not shining, and as I start increasing the value, the brightness of the LED should be increasing as well. And it might not be obvious or very visible in this simulation, but the brightness is really changing. It's just very subtle change. So let's see how this will look like on the real Arduino. Let's copy the code into the clipboard, open the Arduino IDE and paste the code in here, select the Arduino UNO from the drop-down menu and click the upload button. And same as in the walk with sketch, turning the potentiometer will change the brightness of the LED that's inside. Now the potentiometer is not final until we use some nice looking transparent knob. And I was able to get 4 different designs in the different sizes and the different shapes. Here is the smallest one. It's tiny but very transparent. This one is slightly bigger with the top part having the rectangular shape. This one is round and big. It's also not that transparent, it's a little bit foggy. And finally this unusual shape, I believe it's oftentimes called chicken head, and I guess you either love it or you hate it. So once we have everything working, I think it's time to create the simplest possible PCB to accommodate maybe 2 of those, and then you can use it for some real project. I will be using KiGet for the PCB design, and I will not start by creating a new project but rather a new project from template, because there should be a template for the Arduino UNO shield, which will be our starting point. And as I open the schematics editor, there should be already pins for the Arduino UNO. I will just rearrange them in a way that they resemble the Arduino UNO placing a little bit more, so I just move them to the left side and rotate them using the R key. So this is the bottom row of pins, and I will do the same thing for those pins. Again, move them to top and rotate them in a way that they resemble the Arduino UNO board, just like this. And then I want to add 2 potentiometers together with the LEDs and the resistors, so I'll click this button for placing a component, add a symbol, type in LED, and the generic LED is fine, so click the OK button and place it down here, and also second LED around here. Then add the resistor, just typing the R will give us the generic resistor, again place it around the LED around here and also around here. And finally we want to have some potentiometer, so type in potentiometer and click the OK button and place it down here and also around here. Now I want to keep the placement similar to the placement on the PCB, which might not be the ideal case because there will be a lot of wires around, but it just helps me to visualize what's going on. So I'll rotate the resistor for those LEDs, and then I want to use some digital pins, and the digital pins with the PWM signal has those double asterisk symbols in there, so maybe I will use the pin number 3 for the first LED, so pin number 3 like so, and for the second LED I can use for example pin number 5. Again, this also has a PWM signal, then connect the LED to the resistor and then connect both to ground, and the ground is down here, so I will connect those to pins 6 and 7 like so. Now for the potentiometers, for the signal, which is pin number 2, we can use any of those analog input pins down here. So for example, for the first potentiometer, let's use pin number A0. And for the second one, let's use pin number A1. And then same as inside our sketch, I was using pin number 1 to be connected to ground. So this is the ground, so I can also just connect it to this wire, as well as this to the ground. And then pin number 3 to 5 volts, which is down here. So 5 volts is connected to pin number 5, I guess. So I'll just connect pin number 3 to 5 volts. And then this pin 3 for the second potentiometer should be also connected to 5 volts. And I think that at this point we have everything connected. Before assigning the footprints, we need to annotate the schematics. So all those components has unique IDs, unique numbers, by going into Menu Tools, Annotate Schematics. If there is any existing annotation, I will keep it, and I want to sort it by UI position. Click the Annotate button and Close button. And now I have the resistor R1 together with the LED D1 and the potentiometer RV1, and then the second group of R2, D2 and RV2. Let's assign the footprints by going to Tools, Assign Footprints. And we already have some footprints assigned for those pin headers, but we need to assign the footprint for the LED, resistor and the potentiometer. Now the LED should be simple because we are using the LED in the size of 3mm. So I will open the LED through-hole section and search for the 3mm LED. And just in case, I will select View Selected Footprint. And in this window, I can also click this window, which will show me a 3D model, which looks something like this. And I think that we can use this footprint. So I will double click it for both LEDs. Now for the resistor, I will also open the resistor through-hole group, and I've measured the resistor that I have, and the length seems to be around 6.3mm with the diameter of around 2.5mm, and you can see we have different footprints with the different sizes, going from the very short one to very long one. I will select the one in the middle with the length of about 10.1mm. Again, double click it for both our resistors. The final step is assigning footprint for the potentiometer, but I don't think that there's any potentiometer that we can use because we don't have the same size. So I will try to find the footprint that is at least a little bit similar, meaning it has a similar shape and the number of pins, and I think that this one is quite similar. We also have 3 pins down here, and we also have 2 pins for holding the potentiometer in place. So for now I'll assign this one, click the OK button, close those, then save the schematics, and we can go to Tools, Update PCB from Schematics. In here, click the Update PCB, click the Close button, and we now have LEDs, resistors, and potentiometers. I want to have the LED one on the left side as well as the potentiometer, which will be rotated something like this. And maybe I will put the resistor up here. And then for the second LED, again in the middle, then the potentiometer outside, like so, and the resistor on top. Obviously, we are still using the wrong footprint for our potentiometer, so we'll just fix it and create the correct one. But other than that, I think that this is kind of layout that we can use. So for now, let's go to the main KiCad window, and in here select the footprint editor. The footprint that we are currently using is inside potentiometer's through hole, and it's this alpha RD whatever single vertical. This is the one. So I'll right click and select Save Copy As into my own library, and let's just call it pot alpha transparent, because it's also the alpha brand. Click the Save button and then open it by going into this library and double clicking the footprint. Now I want to do a few things in here. Obviously the spacing is wrong because our potentiometer is much bigger, but I also want to select everything and rotate it in a way that it's facing the same position as our potentiometer and try to put it inside the middle of the document, so center it like so. And I was able to find a PDF file with the datasheet for my potentiometer, which is from the brand Alpha, and I believe this is the one that I'm using, but unfortunately not all distances are listed in here, so I ended up just measuring the distances from the sample PCB that I have, the red one, and just using those distances. Then inside the footprint editor, I will select the pad, open the properties and set the new position. For example, for this one, I've measured that the position X should be -4 mm and the Y should be 11. So you can see that our potentiometer is really much bigger, and continue like this for the other pads. The 2 pads that are holding the potentiometer in place has the position about -7 and 0 for the Y. They are slightly bigger, around 4 mm, and the hole inside should be around 2.2 mm. At least that's what I have measured in the sample PCB. And of course I will use the same values also for the right one. So something like this. I've also added labels to mark those individual pins, so ground, signal and VCC. Or 5 volts. And then of course move those silk screen elements to accommodate for the different size for our potentiometer. And after a little bit of tweaking, the footprint might look something like this. Now this pink rectangle is the code yard layer. Now this usually sets the size of the component and might be used to find out if you don't have 2 components too close to each other. But since we will have the LED inside this potentiometer, it's not that important anyway. So I will save this and close it. Then go back into the schematics editor and assign the different footprints for the potentiometer. So again, Tools, Assign Footprints. And for the potentiometer, we will select our new footprint, which is again this one, Potentiometer Alpha Transparent, for both of those potentiometers. Click the OK button and then Tools, Update PCB from Schematics. Click the Update PCB, it will change the footprints. Click the Close button, and of course we have to rotate those, just like this, to be in the middle. And the second one as well, so it's on the correct orientation. And our updated PCB might look something like this. We just need to tweak the positions, and obviously we want to use the same Y position for both potentiometers. I've used the values of 17 and -26 for the first one, and then 50 and -26 for the second one, and moved the other components accordingly. Now I want to show some design, some kind of tick marks on the front of the PCB, and maybe I will also use a copper layer for this, which means that in the ideal case I want to have all my traces on the back of the PCB. So I will open the presets showing only the back layers and also flip the board view, and then I will select the Rotate Tracks button and start rotating those tracks. So the first signal will go to pin A1, and the second signal from the potentiometer will go to pin A0. Then the 5 volt will go to this 5 volt and also to this 5 volt down here. I will not be connecting ground for now because later on I will add the ground plane. I will just make sure that there is enough space for the ground plane to go inside in this gap. And then for routing the LEDs, this pin will go to the resistor. This pin of the resistor will go to ground, so I'll not connect it for now. But the second pin for the LED will go to the digital pin. I believe this is pin number 3, and this will go to pin number 5. And also I want to connect the second pin of the LED to the resistor. and maybe tweak the route slightly, like so. And I believe that at this point the only pins that we don't have connected are the ground pins. However, I've also realized that all our connections are on the front copper layer and they should be on the back copper layer. So I will select all of those by clicking on some of them and then clicking the U button and continue like this, clicking the U button to select all the connected pieces. Then right click and select properties and change the layer to be back copper layer. Click the OK button and now everything is on the back copper layer. And then we can connect the ground by adding the filled zone by clicking this button called Add a Filled Zone. Click anywhere and select the ground, which is around down here, so the ground plane. Make sure we are still on the back copper layer. Click the OK button and then draw the rectangle around the board like so. Right click and select Close Outline, and then right click again and select Zones, Fill All Zones. And if you zoom in, you can see that those two ground pins are connected to the zone, as well as all the ground pins for this potentiometer, and also this resistor, so resistor in here as well as in here. So I think at this point we have everything connected on the back of the PCB, and I can go to the front layers and do some design in here. But before I do that, I will jump to 3D Viewer and see if everything looks fine. So again, jump to the back view of the PCB and there should be all those traces. And there seems to be no problems, so let's jump back to the front of the PCB. To draw the tick mark, I will select the line tool and then switch the layer to the front silk screen layer and draw the line in here. And you can see that immediately the 3D viewer updates and shows the line. And then we can of course rotate the line and draw many of those to draw tick marks. But what I would like to do instead is to not draw this inside the silk screen layer, but inside the copper layer. I mean in the way that the copper is visible, so I can right click the line and select properties and change the layer to front copper layer. And if I do so, you will see that the line is almost not visible. And that's because this will only draw the line inside the copper layer, but it's also being covered by the mask. So what we want to do instead is to not draw this line in the copper layer, but in the mask layer. So again, right click, select properties and change the layer to front mask layer. And if we do so, we see a hole inside the mask, but we see no copper layer. And because we haven't defined any copper on this front of the PCB. So let's actually do that by adding a new filled zone. I will make sure that I'm on the front copper layer and then select the filled zone layer, click somewhere, and for this one I will select no net, so it will not be connected to anything. Click the OK button and draw the rectangle around the board like this, and then right click and select Close Outline, and then right click again and select the zones, Fill All Zones. And as I do so, you now see a copper layer behind this hole inside of the mask, which could be our tick mark. I will not draw those tick marks manually in KiCad, but instead I will use Adobe Illustrator and draw tick marks in there and then export this as a DXF file format. Then jump back to KiCad and select File, Import Graphics, select my DXF file, import into the front mask layer and set some reasonable line width, for example 0.2 millimeters. Click the OK button and then place it on the correct position, maybe something like this, and now we have nice tick marks. There are just a few more things that I've added or tweaked for the final design. One of those is adding those labels and images inside the potentiometer, because those will not be visible anyway and will help me with placing the components. I've also added those bubbles on the silk screen layer, and those are actually just the rectangles, but if you set the line width to be big enough, you will get those rounded corners. And this is again a rectangle just being rotated. I don't know what are all the supported characters for the use the default font, but it turns out you can use the ohm symbol in there, so you don't have to type in R, you can just put the ohm symbol instead. And then of course the LED is just a drawing being drawn in Illustrator and then imported into the KiCad in a very similar way as the tick marks. So this is the front of the PCB, and on the back of the PCB I've actually tried to apply some hatching for the ground fill. And you can do that quite easily if I go to back layers. And selecting this ground plane, you have this fill type which you can set to hatch pattern and then set all the properties for this pattern. And I really just wanted to see how this looks like. Of course I've added also my logo and some information, but those were just small tweaks. And so with the PCB finished, it's time to send it for manufacturing. Actually maybe not yet. Before exporting the files, I usually like to print the PCB on the piece of paper by going to File, Print. Then just lay out the physical components on that piece of paper to see if the spacing is correct, but this time I've tried something different and I've laser cut it from the piece of paper. Which of course has the advantage that now the holes are in there, so I could just put the physical components into the paper itself. So what I've done is I've exported the SVG file first by going to File, Export the SVG file. And then I've imported the SVG file into the Lightburn application, which is the application that I'm using with my laser engraver. And you can see I have quite a lot of different layers, being the outline of the board, and then of course the individual holes, being the inner part and the outer part, the tick marks, as well as the outlines of those individual components. And for those individual layers, I have set different power for the laser, so the holes inside are all the way through, while the tick marks are just slightly burning the paper. By the way, if you want to know more about laser cutting, I've used this laser in my previous video, where I was creating this wooden clock using the Arduino. I will put the link down in the description. But back to our PCB, I have used quite a thick piece of paper, I believe it's 1 mm thick. But since this is still a paper, there was no problem cutting this with the diode laser cutter. And as you can see, the transparent potentiometer fits in those holes nicely. So once I've confirmed that the spacing is correct, I can go back to KiCad and exporting the Gerber files for manufacturing by going into File, Plot, selecting the Gerber files, the output folder, and then clicking the plot button. And I also need to generate the drill file, so click this button and click the generate the drill file, close button and close button. Then go to the PCBWay website, click the Quote Now button. In here, click the Quick Order PCB, select our generated Gerber files, and pretty much the only thing that I want to change is to change the color of the solder mask. By default it's green, but I want to turn it into black color, and as you can see it didn't change the price, it's still $5 for 10 pieces. So I just need to save to cart and then pay it. And while I'm waiting for the PCBs to arrive, let me tell you something about PCBWay, because they are also a sponsor of today's video. And if you use the link down in the description, you can get 10 PCBs like this one for free, only paying for shipping. And even if you don't need PCBs, PCBWay still offers a lot of different services, for example 3D printing or CNC machining, so it's definitely worth checking out. So thank you PCBWay, and let's get back to our project. The finished PCB looks like this, and at this point the only remaining thing is to solder those header pins, those resistors, LEDs, and the most important part, which is the transparent potentiometer. I've tried to solder the LEDs in a way that they are sticking out as much as possible, to put it inside the potentiometer as much as possible. It's probably visible, but I'm using those foggy, milky LEDs, not the transparent ones, hoping that it will also shine more to the sides and not just for the front. And that's probably the only thing that I don't like that much about this potentiometer. It's just quite hard to light up the knob evenly. You still get most of the light coming directly to you from the front and not illuminating the sides that much. But don't get me wrong, it still looks very nice. I also like those tick marks on the copper layer, and usually with those cheap PCBs, the silkscreen layer is actually not printed using the silkscreen technology. It's just a standard kind of printer, which means that a lot of times you can get much better precision if you put your graphics on the copper layer or in the mask layer. But in this case I was quite surprised that those rectangles are evenly filled. I've done one more thing, and that's this front panel. It's heavily based on the main PCB, but I've removed all the components and only kept the graphics. And I've also put holes instead of potentiometers, so I can just put it on the main PCB. And since I don't need any components and I don't need any traces, I can just put graphics on both sides. On the front side I have those tick marks in the mask layer revealing the copper layer, and on the back side I have those tick marks on the silkscreen layer, and I have to say it also looks very nice. As for the solder mask color, I have used a matte black option, and that's actually slightly more expensive, but it looks great. So that's how you can make your project better looking by using transparent potentiometers, and hopefully this video gave you some ideas for enhancing your own projects. If you have any questions, please put those in the comment section. Thank you very much for watching, and I hope to see you soon. Thanks and bye.